through itself. So what I'm saying is that we are describing self-inductance, and in self-inductance we take a coil, and that coil is connected across a battery, and it has a tapping key over here. So when you tap on the key, the current rises, becomes maximum, and then if you're breaking and making the circuit, so that means if you're pointing this or you are pressing this key, so when you press the key, the current rises. When you release the key, the current again starts falling. So therefore, there is this increase and decrease of current that I am showing this by means of this peak. And in this coil, because you know that current is moving, the direction of current is in this way. So as per our grip rule, the curl of the fingers is representing the current. So therefore the magnetic field has to be in this way. So this is the magnetic field here. And this coil, because we know that whenever there is a coil subjected to change in flux, remember that here the flux is changing because of change in current through the same coil, and therefore this will induce or this will produce an EMF. That EMF will oppose the change in current. That EMF will oppose the magnetic field due to the current setup, or you can say that that changing EMF, the coil will oppose the current change in current through itself. So because the current is going through itself, so we say that this opposition is measure of, or we call it as self inductance. Yeah, self induction. Self means current is changing through itself. If there been a constant current, the EMF or this induction of EMF would not have been there. So therefore, self induction is the opposition to the, or you can say that self inductance is the process of making an EMF that will oppose the change in electric current through the coil itself. So we call it as inductance. Yeah, self induction. So self induction is nothing but is the EMF induced in response to the current that is itself flowing through this coil. So we call this phenomena as self induction. So if you want a formal definition of self induction, you can say that it is the property of a coil by which it will oppose, or you can say that it is property of a coil, property of a coil by which it will oppose any change, by which it will oppose any change any change in current through itself. Okay, remember that there is one more say induction, that's called mutual induction. And naturally in mutual induction there will be a change in the neighboring coil, then you call it as the response by the coil, you call that as the mutual induction. So here the change in current occurs in the coil, the applied current is changing, so therefore the coil responds and sets up a, you can say, a sort of back EMF that will oppose the change in this current. So that means we can say that coil tends to have a stable current through it, or this is the tendency of a coil to have a stable current through it. Now we have say we'll do first coefficient of, I'll call this as coefficient of self induction. Coefficient of self induction. Now what we mean by coefficient of self induction, say for example, in order to derive the expression, we know that now the coil tends to oppose. Now if there is greater opposition by the coil, then we'll say that it has got greater self induction. If there's less opposition, we'll say that there is less self induction. Now this induction, self induction, we can derive an expression for this self induction, coefficient of self induction, and we'll find out what are the factors on which it depends. We know that magnetic flux phi is equal to phi magnetic field is equal to B dot A, or you can write it as these are two vectors and this is scalar, so this is dot product. You can also write it as B A cos of theta, where the angle between theta is the angle between the theta is the angle between the magnetic field and the area vector. So it is say if I'll show it like this, say for example you have got this as the magnetic field, this as the magnetic field lines. Suppose these are magnetic field lines B, and suppose you have kept an area like this. This is the area and this is area vector. This is area vector, but sometimes you can tilt this area. You can tilt this area, and in that case, say for example, if you're tilting it, you can say that angle between them is at the moment theta is equal to 0. Here theta is equal to 0. But if you'll tilt the area in this way, so area vector will be this and magnetic field is this. So therefore you can say that this is theta. So area is a vector quantity. Area is a vector quantity. So therefore we write flux is equal to B A cos of theta. Now I am going to derive the expression for self-induction. So magnetic flux is known to us. So therefore whenever a current is going through the coil, say you were having this as the coil, I'm making this coil again. I'll try to keep the number of turns minimum. This is the battery and this was the tapping key and this is it. This is the circuit. So you were having magnetic field in this. I'm making the magnetic field. So you were having magnetic field lines because direction of current is this. And here this is positive terminal, so current is in this way. And magnetic field here will be in this way. This is the magnetic field. Magnetic field. Let me take some more lines. This will be north face, this will be south face, because of the rule that how to find out the direction of magnetic field. Now because this coil is changing, so that means we'll write the EMF setup will be the EMF that will be set up in the coil. If I'll take one turn, so I'll write E in one turn. I'll write in one turn of the coil. One turn of, say for example, this is here solenoid. So I'll write in one turns of solenoid. Okay, it could be a coil or a solenoid. Only thing is expression for magnetic field are different, but the phenomena is similar. So therefore in one turn of the solenoid, I'll write EMF induced will be, I'll write EMF is equal to, I'm talking about one turn means this turn, say for example. So I'll write E is equal to minus d phi by dt. Phi is magnetic flux and dt means rate of change of flux. So if I'm substituting for flux, so I'll write E will be equal to d by dt of B into A. Remember that A is the area of cross section of the coil. If I'm showing you this area, it is this area actually through which the magnetic field lines are passing through. So therefore you'll write E is equal to B into A. But there is not only one turn, there are some more turns, say 1, 2, 3, or let me assume that there are n turns in this. So I'll write therefore E total EMF induced will be equal to N into E. N is the number of turns in the solenoid and E is the EMF set up in one turn of the solenoid. So therefore what I am doing is that I will substitute for this and I'll write the expression therefore I'll write E is equal to N minus d by dt of B into A. This is EMF induced, and we know that the coil we were having, that coil that was carrying the current, the magnetic field by the coil, that was a solenoid here in this case. Magnetic field is equal to N mu naught I upon L. That's magnetic field by a solenoid. And had it been a coil only, a simple coil, not a length, it is not having any length, then we call it as coil. Had it been a coil only, then magnetic field by the coil. Remember, this is solenoid. So we are developing a case, whatever the case may be, we'll apply accordingly. If it is a say coil, then it is mu naught I upon 2r into number of turns. So if it is a coil, you'll write magnetic field this, and if it is a solenoid, you'll write magnetic field by this. So this is magnetic field due to a coil, and this is for the coil. I'm right here, coil, and this is for solenoid. Okay, so therefore I'll write EMF induced will be equal to, say for example मेरे पास in this case I'm having a solenoid, so I'll write this expression. But had it been a coil means the say coil, I'll show here in the diagram, coil means something like this. These are the turns kept at the same time, but solenoid means this. It does have a length. So in this case we were having a solenoid, so I'll accordingly write the expression for magnetic field due to a solenoid. So therefore your emf could be written as minus n, then d by dt of the expression for magnetic field, that is n number of turns into mu naught into I upon L. L is the length of the solenoid. L is length of the solenoid. So you can also write this as EMF is equal to minus n square, n is number of turns, then mu naught, that's a constant depending upon what material you are placing inside the solenoid, and then di upon dt. So it's n square mu naught upon L as well. Or what you can say is that EMF is equal to uh, we were having area also, because flux may will have B into A. This is B and this is A. So therefore I'll write this as E is equal to minus then n square mu naught A upon L into di upon dt. Now this factor is there, that's a constant, and we call this constant as the coefficient of, we call it as coefficient of self induction. We write it this coefficient as, this coefficient is called now coefficient of self induction. So this is coefficient of self induction. Okay, had it been a coil, then we would have used this expression. Had it been a coil, we would have used this expression, and you could have got similar expression that would have been n square mu naught by 2r instead of L. So expression is this. Now we'll go to mutual induction. So I'll define mutual induction first. Induction. Okay, what we mean by mutual induction is, say for example, we are having two coils now. In one coil, there is change in current, and you will see that the second coil will respond to that. Second coil will tend to oppose that change in the EMF. So that means if there is the tendency by the coil to change or to generate an EMF so as to oppose the magnetic field in the neighboring coil, we call that as mutual induction. So I'll assume again, let's suppose that we have got two coils here. I'll make, say, somewhat coils bigger. Remember, you can take coils as well as solenoid, and if it has got, say, length like this, you call it as solenoid. And let me assume that this is connected to a similar circuit, similar current changing circuit, wherein we have used a tapping circuit, or you can use an AC as well. So this is key, and this is EMF, the cell, and then you have kept close to this one more coil. I'll show one more coil by a different color so that you can identify here the case. Say for example, this is one coil, this is second coil, third, this is the turns of this coil. Let me take again this much only. And then in this second coil, we can keep either a galvanometer or you can keep it open. You will be able to measure the potential difference that is developed here. So we call this as secondary coil. I'll call this as secondary, and EMF induced, I'll call this as secondary EMF. That will be the total EMF here. And now you have given some current through this. The current is this, and that current is then leaving. So that means magnetic field will be in the same way as, so I'll choose a different color for magnetic field so that we should not mix the lines. Magnetic field, this, as you know, will be along this direction because curl of fingers is this. Now when this flux, because this flux has the tendency to go through this coil also, some of line, of course may not be all the lines, but some lines, if they are going through this coil, then we'll say that the this coil is subjected to change in flux. And if it is subjected to change in flux, then what will happen? EMF will be induced in the second coil also. So I'll write first the expression for EMF in the second coil, and then I'm moving over here. So I'll write EMF induced in one turn of the secondary coil. So I'll write E is equal to, sorry, I'll write EMF induced in one turn of the secondary coil. EMF induced in one turn of secondary coil, so I'll write it as ES is equal to minus E D phi P, because the EMF is actually because of the primary coil in which current has been given. The secondary coil is not having any source of current. The EM flux was generated by this, and we are assuming that all the flux is passing. That means these lines are not. Actually, there is a mechanism of making these lines to pass through the second coil, all the lines, and by using a core of ferromagnetic materials. So we are not doing, we are showing that we are assuming that all the flux generated by the primary is going through the secondary coil. This is EMF induced in one turn of the secondary. So I'll write EMF in one turn of the secondary, that is d phi E d phi P upon dt, or I'll write ES into N, number of turns in the secondary. That will be the total EMF. That will be the total EMF in the secondary. That can be written as is equal to NS then minus d by dt of. Now what is the expression for magnetic field? If we are assuming a solenoid, of course we have taken solenoid, so I'll write expression for magnetic field due to solenoid into area. So therefore I'll write magnetic field, that is mu naught I, then N in primary divided by L into area. This was flux due to the second. Of course, here we are having some things that are constant, so we'll be taking those constants out. I'll be taking those constants out. So therefore I'll write Es will be equal to minus Ns Np mu naught A upon I upon L into di by dt. And this constant here, we call this coefficient of mutual induction. We call this as coefficient of mutual induction. This is called coefficient of mutual induction of mutual induction. This is coefficient of mutual induction. I'll quickly sum up what we have done so far. So you can see that this was what you have done. You started with self induction. You started with self induction, and then you described self induction. That means the opposition to the change in current through itself. So that was a single coil is required. And if you are having two coils, then the neighboring coil opposes the change in flux through this. Of course, we have assumed that all the flux generated by EMF is going through the second coil. But sometimes there could be a leakage, and that leakage is to be taken on, that leakage of flux. That means all the flux may not be moving through the second coil. But here we are assuming that all the flux generated by primary coil is going through the secondary coil. Actually, there's a, for example, if you'll keep an iron ore and you keep all the turns over here of one coil, one solenoid, and second here. So that will mean that all the flux that is going through this will go through this also. So that is the case wherein we are assuming that this will be your S1, this will be S2, two coils. Then in that case, all the flux will be passing through. But here we are assuming that all the flux is passing through the second coil. Now, what is the unit of magnetic induction, or unit of mutual or self induction? Because they represent the same things, that opposition or the measure of degree of opposition by which the first coil opposes the change in current in the second or through itself. So it has a unit also, and that unit is, say for example, if I'm writing the unit of magnetic flux, so I'll write unit of this mutual or self induction. I'll write it here. This unit of self induction. The unit of self induction. Okay, we have seen just now that EMF is equal to, say you call it as, say if it is self induction, you have seen that that was n square mu naught then A upon L into di upon dt, and we call this term as self induction. We call this term as self induction, and it is represented commonly by L. This is L. L is the symbol for self induction. Then d capital L di upon dt. So if you want to find out what is the unit of this, unit of L, then it's very evident or very simple to derive it now, what should be its unit, or what should be it in terms of potential difference, current, and the time. So we write the coefficient of self induction. It is written as Henry. The unit of L are, the unit of L, that is L, of course that will be volt, second by ampere. And if all of them are 1, then you call it as 1 Henry. It's HENRY, I'm writing it as only 1 H. So that's a big unit of magnetic induction. So a coil is said to have uh, an induction of 1 Henry if a change in a change in 1 ampere of current in 1 second